Hey folks, welcome to the channel. Welcome to this video. I'm Saptarshi Mukherjee. I'm a software engineer 3 at Google and a computer programmer. So in this video, I'm going to discuss the fourth problem of CSES DP problem set, that is coin combinations 2. And this is a slightly more involved problem than the previous problems. So if you have not watched the previous problems, I would recommend watch the basic DP problem in this playlist, where you will get all the basic DP concepts and when we should apply tabulation, memoization, and other nuances are basically present in that video. Please watch that. And I'd also recommend to watch the previous version of this problem, coin combinations 1, which we have discussed in the previous video. So what does this video basically talk about? It says you have a similar money system of n coins as you had in the previous question of coin combinations 1. You have to tell in how many ways. So basically there are n types of coins. Each coin has some value associated with it. Like some are 2 rupee coins, some are 5 rupee coins, and so on. And now you have to say in how many ways you can reach a sum of x. This is identical to the previous question, but there is one significant difference, which is this particular word ordered. So you have to count the distinct ordered ways to produce the sum of x. So let us see. The question here gets differed from the previous question using the single keyword ordered. You need to count the number of ordered ways. What does that mean? These are the total number of ways of reaching the sum of 9. If you see, the sum of each row is 9. But 2223 and 2322 are essentially the same thing. If we say that, okay, 2223 and 2322, I don't care about the order, then they are the same thing. It's the same thing as 2232 and same thing as 3222. They are basically the same thing. So the moment I say I will take 3 2-value coins and 1 3-value coin, I automatically cover these 4 cases logically. And that's what this question wants. It says count this as 1. Don't count its permutations, its arrangements, different arrangements as separate cases. No, this is one way. Then 225 is another way, then 333 is another way, and so on. So when do we call that two different ways are different? That if we basically sort both of them, then at one point they will mismatch. That is the proof that they are two different ways. Fine. So basically we want this particular list. What is the number of ordered ways? Now the thing is, how do we solve this problem? How do we bring this orderedness? We saw that while we let it remain unordered, basically when we did not pay any special attention to counting the different ordered ways together, it was an easy task for us. We basically said, okay, take 2 or 3 as the last coin and then be blind. Forget what is being taken over there. Whatever is the number of ways, just keep on adding them. So 2, 3 and 3, 2, both of them got added as separate ways. But over here we need to be careful. If we are counting 2 to 5, we should not count 2, 5, 2. So that is the main aspect of this question. If you are counting 2 to 5, you cannot count 2, 5, 2. So how do you guarantee that you are counting only one? There are some ways you can think of, like we will maintain each of them like a string and then we will avoid other alternatives, or we will take each of them, we will see their permutations and then we will subtract them at the end. There are different ways for that. But what can be an easy way? There are 10 to the power 5, or let us see what is 10 to the power 6 can be the total sum, and there are 100 coins. So yeah, what can be an efficient way to do this? So let us understand it. When we say ordered, we basically want that two different ordered ways of the same thing should not come. Like two different arrangements of the same choice should not come. So now let us say which arrangement we are going to choose. That is the first thing. Which arrangement are we going to select? Should we select 2 to 5, or should we select 5 to 2 or 2, 5, 2? So let us say only the increasing one, only the increasing or non-decreasing one, only the increasing order we are going to consider. So any choice that you make, let's say the first choice, 3 2s and 1 3, we are going to choose only in the increasing order 2 2 2 3. So now in the increasing order, if we want to find out that, okay, how many such choices are possible, such that for every choice my first elements are lesser than equal to the next elements, lesser than equal to the next elements, and so on. So then for each choice I can basically say, if I'm choosing something like this, let's say element 1, element 2, element 3, dot 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 element k, then I want this order, that element 1 is less than equal to element 2 is less than equal to element 3, and so on up to element k. Which means with the in regard to the given question, or in regard to this given test case 235, let us see how I can think about it. With 235, many cases are possible, like these three cases are possible. The largest element is 5. We have been looking at the last choice that we can make. Here the last choice, basically we have been looking at every choice from the last element perspective, that what can be the last element. Last element can be 2 or 3 or 5. Now last element can be 2, last element can be 3, last element can be 5. Now this is our last element. This is our last element, and we are looking at the sum of 9. If our last element is 2, that means our previous element must be 2, because we are committing that our array will be in increasing order. We are only considering increasing order choices. So if our last element is 2, previous elements can only be 2. If our last element is 3, previous elements can be 2 or 3. And if our last element is 5, previous elements can be 2, 3, 5. So essentially, if our last element is 2, in that case, we are expecting that give me x equals to 9 minus 2. We have taken 2 already. So give me x equal to 7. Give me sum equal to 7 using only 2. Give me sum equal to 3. Sorry, sum equal to 9 minus 3, that is sum equal to 6, using up to 3. You cannot take 5 because last element is 3, so previous elements have to be lesser than equal to this. So using 2 and 3 give me the number of ways. And when you're taking 5, you're basically saying, hey, the sum is, remaining sum is equal to 9 minus 5, that is 4. 9 minus 5 equal to 4. For this 4, you can take any of these elements, 2, 3, 5. Now let us look at this. What answers are possible? Let us see. For sum equal to 9, when you said last element must be 2, now every element has to be 2. If your last element is 2, you are basically saying I'll keep in increasing order. I'll choose elements in increasing order. That means you are saying if the last element is 2, every element has to be 2, because those are your choices, 2, 3, 5. Now up to 2 you have to keep all the elements. All the previous elements have to be lesser than equal to 2. So now it becomes a problem. You can foresee that sum equal to 7 is not possible using 2. So no cases are possible. Now sum equal to 6 using 2 and 3. What are possible? Using 2 and 3, you know that 2 cases are possible. 2 plus 2 plus 2 and 3 plus 3. 2 cases are possible here. And 5. Now 4 using 2, 3, 5, you know that 1 case is possible. That is 2 plus 2. So using those things, what can we say? Using those things, we can say that from these two, by attaching 3 at their end, we are basically getting by attaching 3 at the end, we are basically getting 2, 2, 2, 3 and 3, 3, 3. This 3 we have attached. The last 3's we have attached. And we have taken the remaining things from there. We have just attached 3 at the end of these two. So we are getting the sum of 9 successfully. Similarly, from here we can basically take this and attach 5 at the end, so we will get 2, 2, 5. That is the answer. So what did we do over here? We basically said if you are taking the last element, or if you are taking any element as the last element, then everything before that should be formed from the elements up to that. It should not be formed from greater elements. So let us see. I believe that the coins are sorted, or if they are not sorted, you can anyway sort these values of coins. Um, or actually you can basically treat them in any order. Here it is 2 3 5. You can actually treat them as 3 4 3 2 5, something like that, basically saying that okay, after 3 2 should come, after 2 5 should come. The thing is, these coins should be in some order. So here we are taking the sorted order. So you can take basically any order, that okay, after you can, if your initial array was something like this, let's say 5 3 4, then you can basically say this, okay, I'll first consider the 5s, then the 3s, then the 4s. Totally fine. So you can move in the way that is given in there. You will say, okay, if I take 3 as my last element, I cannot take the next element. I will take the previous elements or this current element as my previous elements. So that is the idea. That is the idea. Which means now if I look at a slightly, yeah. So basically, if I look at something like this, for the different x, we'll be forming it. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, let's say. And for different values I'll be forming. The values, let's say, are 2, and let us take different values like 1, 2, and then maybe 3 and 5. So first I'll say that just take 1. That is the idea, that first use only 1. So if only 1 is taken, then you basically have, for 0, 0 can be formed in only one way always. 1 can be formed in 1 minus 1 equal to 0 ways. So one way, 2 can be formed in one way. So using 1, you can form each of them in only one way. Now it is using 1. It's simple. It's similar to the previous coin combinations 1 that we did. That if you want to form 3, let's say, so if your last choice is 1, then see in how many ways 3 minus 1, 2 can be formed. That number of ways you can form. You can put 1 at the end, and then that is your number of ways. So basically 1 got copied over here. Now the thing is, let's say we are now saying, okay, you can use 2 also. So now for 2 you have to decide the values. Let's see how we will decide it. For 0 you will not take anything, the number of ways remains 1. For 1 you cannot do anything better. You will say, okay, I can't take 2, and then your answer will come from the top only. So without using 2, whatever was the answer, that only remains. Okay, because you cannot take 2, it is not possible. Still, for any case, this is the this is the situation that remains. Whether you take that element or you not take that element. So let's move ahead and let's see. At this stage, for 2, either you take 2 or you don't take 2. If you take 2, then you can basically keep taking 2. So if you can take 2, then see that by taking 2 or not taking 2, what can you get with the remaining sum? For the remaining sum, you can get, there are 1 ways for the remaining sum. So basically I'm saying that for x equals to 2 and using 1, 2, there are 2 ways. You can take 2 or you will not take 2. If you take 2, then you will remain with x equal to 0, and you can use 2 or not use 2, it's up to you, because you have taken 2, so previous elements can go up to 2. And if you don't take 2, then your x remains the same because you have not taken that element, and now you cannot take 2 because you have declared, I have not taken 2, So I will not take 2. Basically 2 will not be my last element. That is your declaration. So these are the two cases. So let us see where they should go. This one, 1 and 2, same choices, x equal to 0. So go to the 0th column. Go to the 0th column. 0th column, 1 to 2. Go there. And the other part is x equal to 2 but using only 1. Go above. Take it from there. Go above. So you have one way of not taking this 2 and still ending up at the x, and you have one way of taking the 2 and getting the other part using up to 2. So basically 1 plus 1 gives you this 1 plus this 1 gives you 2. Similarly, for each one of them, we will get it as the sum of this and the left, x minus 2. So 1 plus 1, 2 over here, then maybe 1 plus 2, 3 over here. What are the three ways for 4? The three ways are 4 ones, 2 ones and 1 2, and 2 twos. So those are the three ways. Similarly, we'll have three ways over here. 1 plus 2, 3. Then here it should be 4, 4, 5, 5, 6, 6. Something like this. So 11 can be formed in 6 ways using just 1 and 2. And we are only looking at the sorted order. So if I take this example, for 5, how it is 3? The three examples are 1, 1, 1, 1, 1, 1, 1, 1, 2, 1, 2, 2. These are the three examples. There is no other example possible. Other than just rearranging them, there are no other ways possible. These are the only ways. Right? For 3 also we will do the same thing. The initial ones, let's fill like 0, 1, 2, there are no ways, so copy the top ones. Right? And then for 3 I can say, hey, I can take 3 or I may not take 3. If I take 3, then my answer will come from here. If I take 3, then 3 minus 3 is 0, that is this particular element matters then. And if I don't take 3, then I'll basically say, okay, then up to 2, what is the way? So we take, what is the number of ways? It is 2. So 2 plus 1 gives us 3. And similarly, we'll have 1 plus 3, 4, 2 plus 3, 5, and so on. Let us take this particular example. Here also same way. Over here, if I don't take the 3, for 6, if I don't take the 3, then I will get 4 ways. There are 4 ways if I don't take the 3. If I don't take the 3, using only 1 and 2, there are 4 ways. All the 6 are ones. All the 6 are ones. Or you use a single 2, or you use 2 twos, or you use 3 twos. Those are the 4 ways. Yeah. And if you take a 3, then you will say, okay, I have taken a 3. Now tell me, before me, you have to place the sum of 3. Before me, the sum of 3 needs to be placed. How many ways are there? These are the number of ways. How? You can basically put 1, 1, 1. You can put 1, 2. And you can put only 3. In that way, you're getting 3. So 3 can be formed. This 3 can be formed in 3 ways using these elements while retaining the order. So that same thing we are using. That same thing we are using over here. So okay, if I'm using a 3 over, if I'm opting for the 3, allow the 3 in the previous elements also. Allowing the 3, I'm getting 3. And if I don't take 3, then that means previous elements, if my last element is not 3, then I'm basically saying use smaller elements and fill it up. Using smaller elements, I already know the answer, that is 4. So here we are using the states really very intelligently. So the answer turns out to be 4 plus 3, 7. Similarly, 8. Then 5 plus 5, 10. 5 plus 7, 12. 6 plus 8, 14. And 6 plus 10, 16. And then finally 5 comes. 5 will also say the same story. So from 0 to 4, no possibility of taking 5, so copy the above ones. So 1, 1, 2, 3, 4. And then comes 5, and 5 comes and says, hey, I can take 5, in which case the answer comes from here, or I can choose not to take 5. The answer comes from the top. 1 plus 5 gives us 6. and the process continues. 1 plus 7, 8, 2 plus 8, 10. If I show this last example, for for x equals to 8, how many ways are there? It will be 1, 2, 3, 1, 2, 3. So this particular thing plus this, 10 plus 3, 13. So 10 using 1, 2 and 3, you can form 8 in 10 ways, let's say. And using 5, you can form the sum of 3 in 3 ways. You cannot take 5 definitely, but taking up to here, you have all these choices. You can form it in 3 ways. So that's it. You have 3 choices from the left, 10 choices from the top. You get 13 in total. If you use 5, then there are 3 choices. If you don't use 5, then there are 10 choices. That's what you get from here. Similarly, the process continues. You can fill up this table. Right? So in this way, we can basically say, first of all, we need to understand what our DP states mean. This is our DP table. So here dpij is basically, I'll call this my I and I'll call this part my j. So basically, I want to know that what is the number of ordered ways to get sum or x equals to j using, so the values of I will be basically the indices 0, 1, 2, 3, whatever are the indices. So using AR of, that is the coins array, AR of 0 to I. Using those coins, what is the best thing we can get? That I am storing in dpij. So now what is my answer? My answer is this last element. That is, whatever x is given to me, the answer will be dp of using every choice, that is n minus 1 up to the last coin we can use, and we have to form the sum of x. So this is my final state. This is known as the final DP state. Final DP state. Yeah. This is my final DP state. And then we need only one thing, that is a recurrence. So we will say dp of ij. ARI is my maximum element. So I will say that either take ARI or you don't take ARI. If you take ARI, then how many choices you have? You have ARI j minus ARI. You have DPI j minus ARI. And if you don't take ARI, then basically you will never take ARI. You're not choosing that as the last element. So you'll say, okay, using the previous elements, I minus 1, what is the number of ways to get the sum of j? So this summation will give you the answer. So basically dpij is equal to dpij minus AR of I plus dpi minus 1 of j. In which order is it going? We are depending on the previous things in the row and the previous row. So we are depending on the values for the smaller i's and smaller j's, which means we should start filling the table from the lowest values of I and j. That is the idea. So the moment the orders are clear, mostly we have discussed this in the common DP class, that if the order is clear, in what order we will keep on getting the answers, which answers we need before which answers. For example, this answer depends on the left and top. So definitely I need to proceed from the left to the right. I need to proceed from the top to the bottom. Then only I can get this answer from the already solved things. So you need to decide upon this order. When this order is clear, you can apply tabulation. So this is your recurrence. Now, taking it one step ahead, if you look at this, if I don't store the previous row, when I come to the next row, do I need the previous row or not? That is one question we always ask. Before that, how to implement this? We can basically write two loops for increasing I and increasing j. So basically for the outer loop can be on I, that is uh, the coin's value, and this the inner loop can be on j. So it will go through the sum. So our code will basically look like this. For I goes from 0 to n minus 1, and for j goes from 0 to x, and we are basically saying something like this: dp of ij is equal to dp of uh, I minus 1j plus dp of I j minus ar of I. So in this way we'll get the answer, but you need to do some validation check. So validate that I is greater than equal to 0 if I greater than equal to 0, and here also you should validate that if j is greater than equal to ari. So within this validation you can do it. If I is not greater than 0, then don't take anything over there. Take that as 0. Take this term as 0. Nothing comes from the top. Similarly, if j is lesser, then take this term as 0. So that way. In this way, in 2-3 lines, this problem can be done. But first of all, how much space is this taking? This is taking a lot of space. 10 to the power 6 into 10 to the power 2. If you look at this particular state, dp of n minus, for reaching this state, we know that these values can grow very large. This can go up to 100. This can go up to 10 to the power 6. So total there are 10 to the power 8 steps, which is very large. Space complexity is very high. So then the question arises, can we improve the space complexity? So this is a very interesting DP strategy of 2D to 1D transition. 2D to 1D transition of DP. So let us look at this. We basically did this computation. We required all the rows. We have seen the computation. But now if I say that, hey, if I don't give you the luxury of so many rows, there are two strategies here. You use two rows, you alternate between them. We will look at that during some other problem. Here I will try to solve the problem using one row only. How can I do it? Let's see that. So for the first row, I know that this is my answer. This is for I equals to 1, or I equals to 0, let's say. I equals to 0, for which the answer is, the value was 1. Value, that is the coin's value, was 1. Now I come to I equal to 1, and I'm having the value 2 over there. We know we will do those operations, but observe one thing. We are essentially, up to a point of time, we are just copying the top values, which is 1, 1, which means we are basically doing nothing. The top values are the bottom values, and then from here, what are we doing? We are basically adding these two values and putting over here. So if I say, instead of adding and putting over here, why don't you change this one only? From any element, look at it. When we are basically going in this row, when we are basically going in this row, let's say we are at this particular element. When we want this element, we are only looking at our top element. So if we store in the same array, if we don't store in multiple rows, if we store in the same row, which means I'll just overwrite that row when I'll go through that row once again. I'll just overwrite that row. Will there be any problem? No, because what is over here, what am I doing? I'm basically saying that previous row same column value, that is the top value, this is the top value, plus the left value. So instead of top value plus left value, you can say current value plus left value. If you have only one row, you can basically say that. So let us see how it happens. So instead of multiple rows, now I'll have only this row, only one row, and I'll have these things there. Yeah. Now I'll go from left to right and see what happens. Now I'll consider that I'm using 2. This was with respect to only 1, only the coin 1, but now I'm using 2 also. That's okay, up to 0, 1, nothing changes. From 2 onwards, increase this by this 1. So go 2 level before. This is up to 2 you're basically taking, up to 2 means this 2, up to this 2 you're basically taking that what are possible, up to this particular coin, what are possible, that answer is 2. So now just add it over here. So you have 1 plus 1, that is 2. Similarly, just add it over here. You have 1 plus 1, that is 2. And similarly, just add this over here. You have 1 plus 2, that is 3. Instead of looking up, add to the own element. Look at this. When you come to this element, this is essentially what your previous row left for you. So here, the introduction of this row with the previous row is not that complicated. That's why we can say that no need to store them as separate rows. Keep overwriting this row. You can see that this row is itself getting overwritten. So now if we look at this particular iteration, here we are saying go to the left. This is the left in the same row. This is the left in the same row. So we are already forming that we are coming from left to right. So the left has got updated. We have this in the same row. And this one is basically the same column. Before we came over here, the same column was left by the previous row, by the previous coin. So we are just going to continue with that value. So if we carry this on, we will see we'll have the same trend 4, 4, 5, 5, 6, 6. Now let's say we start the next iteration with 3. Now we are starting with 3. So in the same way, if we run from left to right, up to 2 nothing changes. Then with 3 we will say, okay, take this value your previous row had given you. Logically, you know that your previous row has given you are storing only one row, but you know that okay, this row contains the authentic state. So now go back by 3 places and add to it. So 1 plus 2 gives you 3. Similarly, 1 plus 3 gives you 4. And instead of storing it separately, just replace it. Because nobody wants the previous value now. Everybody later will want the new value. So how are we deciding this? We are deciding this by this particular dependency pattern, that for this particular element, I want the previous element and the immediate top element. So this top element is nothing but this element before you are doing this change. Which means if you are just storing one row, that is also sufficient. For this element, you will say, okay, add this previous element to itself, and that gives you the new element. So instead of depending on anything like that, you can just say, hey, go from j equal to 0 to x or whatever, instead of dp I minus 1j, just forget I. Just forget I minus 1. So this is not needed. dpj plus dpi. That's it. dpj contains the previous value. Before this change, it contains what the previous row left it with. And j greater than equal to ARI, we need to check that. That's it. So basically, we don't need that extra state. We don't need so many rows. Our space complexity, we basically need a 1D array. Now our space complexity drops to big O1. This is big O1 space complexity. Time complexity remains the same, which is n into x. For these problems, we are having the same time complexity, which is number of choices multiplied by the sum, n into x. So it's a simple loop. And if you compare with the previous problem, in the previous problem's solution, we basically saw we kept x as the outer loop. We kept x as the outer loop. But over here, we basically kept n as the outer loop. Over there, we kept x as the outer loop because we said that for every x, find the entire thing. But here, the ordering matters. So we are basically saying, okay, first consider that you have only one coin. Then consider you have another coin. When you have a bigger coin, then you need to make the firm choice. Will you keep it or will you not keep it? If you keep it, then if you want to take that extra coin, the bigger coin, then this is something that you want. This is your number of ways. If you don't want that coin, this is your number of ways. Add them up, you will get the total number of ways up to that coin. So you saw how we first looked at the problem in a 2D way, and then we improved our complexity to basically finish up in 1D way. We have seen the improvement in space complexity and time complexity. The previous approach was basically big O n into x space complexity and n into x time complexity. So definitely we have improved the space complexity by this 2D to 1D transition. This is our 2D to 1D transition of a slightly rare type, for which you have to be really smart about your algorithm, about your ordering, and about the problem at hand. So not very trivial, not very common, but it's good to know. Let me know if you have understood this problem. Let me show you the code. So there you go. I've just taken 1D array. After a point of time, it becomes like a practice. You can do the 1D version directly. So then you basically go through the n different coins in any order, but in a particular order. In any order, but in a particular order. It can be ascending, it can be descending, it can be any other order also, but you cannot change the order in between. So stick to a particular order. It can be any order. Yeah. Now it's basically you're going from 1 to x. Why not 0? For 0 also you can go. It's the same thing, but answer 0 equals to 1. Nothing changes for answer 0, so that's why it's taking from 1 to x. And then this is the val, this is the jth item. Here I've taken j as that thing, but it's basically, yeah, it's the same thing. So you take the jth item, and then if the value is less than equal to I, well, that is Cj, if it is less than equal to I, then you can go for that. Basically, you can take that coin because the coin is not bigger than your current sum, current target. That's what we are checking, and the modulus thing. Finally, you just return the last case, answer x. Over there, we have seen that the final value over there was dp n minus 1 x. Here n minus 1 goes away. dpx gives you the answer. So then you will just return answer x or dpx. That's it. This was a slightly tricky problem. I hope you understood the solution. Let me know if you have felt anything difficult or if you have confusions in any part. And if you have found it informative, please do share with your friends. And yeah, let me know if you want any other kinds of videos. Till the next video, take care, keep coding, and see you all in the upcoming videos. Bye.